lunch webinar of the KIVI, the Royal Dutch Association of Engineers, Department Electrotechnical Engineering. Today the topic is CERN high voltage, mid voltage grid network based project in the Large Hadron Collider. My name is Koos Koster and I will be your moderator for today. The technical support is by Paul van Moerkerke. First, some house rules. Please switch off your camera and your microphone. If you have any questions to the speakers, please put them forward through the chat facility in Teams, preferably in English, but also can also be in Dutch. We will put the questions at the end of the presentation to the speakers. This session will be recorded and will be published on our YouTube channel. If you watch this webinar, you agree with the recording and the publishing. In short, I will tell something about our association. We are the leading association of engineers in the Netherlands and we are existing for more than 175 years. Our association is committed to the interests of engineers and technical professionals in the Netherlands and Netherlands overseas. Look further on kivi.nl what we organize as an association, or even better, become a member of the largest engineering association in the Netherlands. Then you will stay informed of the latest technological developments about, for example, the energy transition, and you can participate for free to our lunch webinars in addition to all kinds of other activities. The subject of today: European project targets better energy efficiency at CERN with improved grid monitoring tools. Particle accelerators are energy intensive, consuming to hundreds of gigawatt hours annually, comparable to small or medium-sized European cities. This, combined with the reliance on non-renewable energy sources and significant raw material requires pose environmental challenges. This is why the Research Facility 2.0 project, funded by the European Union Horizon Europe program and the Swiss State Secretariat for Education, Research and Innovation, is exploring innovative solutions to make accelerators more sustainable. I will give the stage to Alice Maffezoli from Zaphiro for the presentation. She will introduce herself and the other speakers of today, Isabel Aguillo from CERN and Jeroen Boekhout from ELEQ. Alice, the floor is yours.
Thank you, Koos, for this introduction. So good morning, everyone. Thank you for your interest. I think I speak for all three of us. We are happy to be here and share some insights about the contribution of our companies and institutions that are CERN, Zaphiro and ELEQ to this project. I will share some slides. Please let me know.
I can see them.
Good. So before introducing the other two speakers and myself, let me just give you an overview of the project first, and then Isabel will go more in details. So the project RF 2.0, that means Research Facility 2.0, is our Horizon Europe funded project that aims to design, develop and validate novel solutions for components and systems that allow transform particle accelerator in more sustainable and energy efficient infrastructure. In here, I would like to focus a little bit more on the fact that this is a private grid operator. So the challenges that we face in this project are very applicable to other private grid operators rather than public utilities with which we are used to work. So this project is also applicable to other applications such as medical centers, data centers, so on and so forth. The project has started in 2024, is targeted to end in 2026 for a total duration of 36 months and with a budget of 5.6 million euro. And there are some partners of the consortium that you can see in this slide. The project has different focuses that are represented by different working packages, and in particular we are focusing on working package number 4. So some introduction about the speakers. I will start with myself. My name is Alice Maffezoli. I'm the Sales and Business Development Manager at Zaphiro. My academic background is in electrical engineering. I have a master in electrical engineering from the University of Pavia. with specialization in robotics from VIA University in Denmark, and I have an executive master in business administration from Polytechnic of Milano. And my professional background is more in medium voltage variable speed drive systems in the oil and gas sector for ABB, and later in hydrogen and fuel cells, and now in smart grid technologies. So I give the floor to Isabel and Jeroen for their introduction.
Thank you, Alice, and good morning, everyone. My name is Isabela Mundarain. I'm an electrical engineer at CERN. I studied my bachelor's and master's in industrial technologies engineering in the Polytechnical University in Madrid, and then master's in energy systems in Illinois Institute of Technology. After that, I worked for 4 years in the DS in Exelon in Comet, the DSO in Chicago and Northern Illinois, as the responsible of distribution planning for 2 areas, including the O'Hare Airport. And September last year, I joined the electrical engineering project management section at CERN for working on the research facility 2.0 project. Thank you.
Thank you, Isabel. I'm Jeroen Boekhout. I am currently 4 years at ELEQ. I have also a background in electrical engineering, a bachelor in electrical engineering with a specialization on energy grids, and then a master management of innovation to really be a strategic partner between technology and management. I've been in offshore, I've worked for Siemens, and I'm currently product development manager at ELEQ to help find innovative solutions for the challenges we currently have in our energy grids.
Thank you. So we're going with a brief agenda. So the idea is to give you a brief overview of our companies and institution, and then to do a deep dive on the project. So first with CERN presenting the overall project, and then with a focus on PMU technology and PMU installation at CERN from Zaphiro, and closing everything with ELEQ contribution to the project. So the customization that has been done together with ELEQ for the measurement devices. And we will close everything with a demo of the dashboard. So what is available at CERN today. So I give the floor to Isabel that will start this part.
Thank you, Alice. Yeah, so Alice already gave a brief introduction of the RF 2.0 project. I want to start talking about CERN in case someone over here is not very familiar with it. So what's CERN? It's the world's largest particle physics laboratory. It was founded in 1954. And it's located in the border between Switzerland and France, near Geneva. The mainly goal or mission of CERN is to study the fundamental particles that make up the universe. And for that, we use advanced instruments and technologies like the particle accelerators and the detectors. Over here, you can see the accelerator complex of CERN, from the linear accelerators on the bottom all the way up to the LHC, the Large Hadron Collider, which is the biggest and most famous accelerator at CERN, which is used to collide particles at high energies to explore the basic building blocks of matter. CERN operates primarily funded by,
Sorry.
No worries. Primarily funded by its 23 member states, with additional funding from other organizations internationally. And the biggest achievements are the invention of the World Wide Web, as you all know, in 1990, and as well as the discovery of the Higgs boson in 2012, which is a key part of the standard model of particle physics. You can go to the next slide, please. Thank you. So I wanted to start by giving an overview of the electrical grid at CERN. Over here, you can see the 400 kilovolt infrastructure, which is a very strong network, good for demanding power users like CERN in red. There's over there in the middle where it says BT, that's the main substation, Bois de l'Eau, which is owned by RTE and the French grid operator, and has 3 links to Genisia, which is to the left, and it's the strongest one, and 2 more to Berrois, Chamonton, to the down there and on the right. From Bois de l'Eau, it's the main feed of 400 kilovolts to the 2 main substations at CERN, which are B1 and B2. Where we step down the voltage from 400 kilovolts to 66 and 18 in B1 and to 66 kilovolts in B2. From there, there's a radial network of lines that start next to B1 in a 66 kilovolt substation, and that go to all the even points of the LHC loop, as well as point 1 and the main sites of CERN, which are Mede and Trefzin. Yeah, so those are the dark blue lines that you see that end in dark blue point, which are the substations providing the 18 kilovolts to the different, the substations transforming 66 to 18 kilovolts into different points. Staying on the, well, yeah, that's the long story short. Then going inside the project more in detail. So already Alice introduced a bit what the project is about. It's important to keep in mind that the main motivation of the project is the environmental challenges that particle accelerator pose, with the accelerators being very energy intensive and relying on non-renewable energy resources as well as raw materials. Just to give a bit of reference, particle accelerator can consume up to hundreds of gigawatt hours annually, which is similar to a European medium-sized city. And well, in the beginning of the project, the partners identified different bottlenecks towards the RF 2.0 goal of making research facilities more sustainable with a multidisciplinary approach from the component to the system level, as well as involving both physics and energy engineering topics. Consequently, the project focuses on 4 main points, which are in orange, developing highly efficient components as permanent magnets, semiconductor technologies, and solid-state amplifiers. In blue, integrating AI-assisted energy management systems. On the bottom, in purple, adopting low-carbon technologies like energy storage systems and renewable-powered computing centers. And on the left, in green, and the one that applies the most to our work package and what we're going to be discussing here, improving power consumption flexibility and network services through innovations in power electronics, DC networks, and fast measurement devices units as the PMUs. You can go to the next slide, please. Thanks. So as you can see here, the project brings together CERN and Zaphiro with KIT and other 7 partners, including some of the largest particle accelerator facilities in Europe. And each partner focusing in different of the main focus points that we mentioned before within different work packages, and with a final demonstrator that it's aimed at the end of the project for each of the main topics. For most of them, we are still in the modeling and testing stage. In fact, for the PMUs installations at CERN, they were done in advance in comparison to the planning because of some operational constraints internal from CERN, which didn't allow us to install those PMUs anytime we wanted. So we are ahead of time. So regarding the CERN contribution to the RF 2.0 project, the electrical distribution systems in particle accelerators, and of course also at CERN, typically use standard SCADA systems, which have a slower dynamics. So that's why the deployment of the PMUs will provide some benefits to us, starting with analysis of perturbations coming from the upstream electrical transmission grids, the ability to better understand how those perturbations impact our equipment, our different subsystems and components, and eventually to increase the grid resiliency by attacking the specific identified weaker points, and of course to provide guidelines for future accelerators, in particular, for example, for the FCC, the Future Circular Collider. If you can, yeah. As for other aims that CERN has with the help of the PMUs, which is capable of monitoring voltage and current fluctuations in real time, with also a lot of accuracy and high sampling frequencies. We want to create, or we are in the process of creating a digital twin with KIT that it's being fed that is aimed to be fed with the information monitored by the PMUs. So it's going to be a real-time machine where the digital twin runs will be fed with the PMUs data. Also, another objective is the monitoring the power quality of the grid and perform harmonic content analysis again, as in the previous slide, with the aim to better understand and classify the different disturbances and identify mitigation actions and possible optimizations to increase the efficiency of our power grid. And lastly, we have an objective of communicating the detected events by the PMUs to our SCADA system. It's also an important goal for the grid operators, mainly, to react to certain events. You can go to the next slide. Thank you. So focusing on the PMU installations at CERN, we installed a total of 24 PMUs, 2 in the 400 kilovolt network, 2 in the 66 kilovolt network, and the rest in the LHC loop, as well as another one in the computing center, with a special focus on one of the experiments, which is ALICE, which is over there marked on the right, with a total of 9 PMUs being installed there, where we plan to monitor all the different types of loads. Over here, you can see an example of one of the PMUs that we installed in BE1. On top on the left, you have the front of the PMU, and then on the right, you have the back part where you can see the different pins for everything that we're monitoring. On the bottom, you can see some of the CTs that we installed for the current measurements inside of the racks of the release, and that's pretty much it, just as an example. But now my colleagues will go more in detail on the PMU's structure and installation. Thank you.
Thank you, Isabel. So I will take over for the part of the PMU. I'll go a little bit more in detail about the PMU technology, but first I will give you an introduction of what is Zaphiro, who is Zaphiro, and what we are doing here. So Zaphiro is a Swiss company founded in 2017 that is based in Lausanne in Switzerland with a subsidiary in Italy, and with a global presence thanks to the support of a network of business partners worldwide that acts as our value-added resellers. So at the moment, we have deployed our technology worldwide with a major presence in Europe, with more than 20 installations, 20 customers, for a total of more 300 devices installed. Our major investors are ABB and CDP Ventures. So to start about PMU, so what are the challenges in modern grids? So there are mainly 2 challenges. The first one is the integration of renewables. So as we all know, they are changing the way we operate our distribution grids and grids in general. So the first one is definitely the need of integrating the renewables, so congestion management and having real-time visibility, and also managing the capacity of the grid. The other problem is outages. Outages that can come for several reasons, like extreme meteorological conditions or aging of the infrastructure, so on and so forth. So these are the 2 main challenges we see today. So we tackle these 2 challenges. These are real cases, real news, and you can see that one of them is not far from you. And the other challenge that we tackle is the monitoring of power quality. And this is exactly the focus of this project. So this is where we will focus more in this presentation. So we have a solution for these 3 problems thanks to our technology. So at Zaphiro, we have developed the first integrated hardware and software solution based on the PMU technology for distribution grids. So our hardware is called the SynchroSense, is a measuring unit based on the PMU technology. I will go through the technology in a moment, but basically they are very fast information, high quality measurement, and done with time synchronization. So thanks to this fact, we don't need to install PMUs in all the grid. We just need to select some critical point of the grid to have a full observability of the complete grid. And then we have our software, our platform that is called the SynchroGuard, that gives information about the status, real-time status of the grid, that gives observability, congestion management, power quality information, and also faults, so faults location and detection. Without going too much into details, we basically serve operation people for the real-time visibility and for corrective and predictive maintenance, and we serve also asset managers because we give some trends and information in order for them to plan the future grid. As a side note, we are also working on project based on artificial intelligence and machine learning that will enable predictive maintenance. But now to go in details about this project, so I will give you some overview from a technical point of view of PMU technology. So PMU is a phasor measurement unit. A phasor is a complete information of a waveform. So it's not just amplitude, but also phase and frequency. And we do this measurement at a very high speed rate, every 20 milliseconds. And these measurements are time synchronized, for example, with a GPS antenna, with a GPS signal. So thanks to this high quality, fast, and time synchronized information, as I said before, we don't need to install measurement everywhere, but we select some critical points and we can have full observability. What is the advantage of PMU technology versus the traditional technology is that the measurement is of high quality because we basically follow the frequency of the waveform, so the 50 hertz, and we also have time synchronization. So regarding the project at CERN in particular, and this is also what Isabel said, the main KPIs for success were the functionality validation of the PMU. So as we had 3 years to install the PMU, we are ahead of schedule just because the commissioning had to happen quite soon in order to start to have data, and I will show it later in the dashboard. And then we had to validate the data accuracy and reliability, and in general to provide a dashboard that was user-friendly and easy to use for operators. And also the SCADA integration was also something that was very relevant for this project. Just to go a little bit more in details for what concerns the electrical part. So here represented is the single line diagram of CERN electrical infrastructure. We can see the 3 different voltage levels that Isabel was describing, the 400 kV, mainly supplied by the French grid operator and with some critical loads backed up by the Swiss grid operator from the city of Geneva. Then a step down to 66 kilowatt and a step down to 18 kilowatt. And the LHC is supplied at 18 kilowatt. And unfortunately, this single line diagram is a very high level single line diagram. So it doesn't really show the beauty of the electrical infrastructure, but all these substations, they all supply transformers, motors, data centers. So that's why also the complete observability is quite important and the power quality monitoring is quite important in this project. And this, I emphasize again, the use of PMU technology for power quality monitoring in a private grid operator that has some characteristics that are quite different from the standard grids that we can see from utilities. The network is composed by 2 primary substations and 8 secondary substations. We have installed 24 PMUs, and the infrastructure consists not only on the electrical part, but also on measuring equipment and IT infrastructure. In standard grids, with our SynchroSense, we rely on voltage measurement and current measurement in the primary substation and only current measurement in the secondary substation. But for this project, as there were already available current and voltage measurement, and also for the peculiarity of the project and for the aim of the project, so the power quality monitoring, in this case, we are monitoring current and voltages everywhere. The time synchronization is done through a GPS signal, so we have some antennas installed outside the substation. And thanks to the GPS signal, we can do the time synchronization. On top of that, we have SCADA integration. The SCADA integration integrates some alarms and some information about the events, and then the dashboard, our own dashboard, can be opened to go more in detail about the information of the power quality event. So the installation of PMU at CERN, together with the commissioning of the SynchroGuard, as the primary focus on the power quality. So it enables CERN to better understand the power quality events happening in their grid. Power quality events are mainly divided into 2 categories, so continuous power quality event and temporary power quality events. So the continuous ones are voltage variation, voltage imbalance, power frequency variation. The temporary ones are rapid voltage changes, voltage dips, voltage interruption, and overvoltage. And I will later show a demo on that. And this is a brief introduction of how the measurement is done. Then ELEQ will go more in details about that because it's their contribution to the project. But here the main technical challenge was that we had to find a good solution for the retrofit of CERN substation because the deployment of new voltage and current measurement and sensor was not allowed. So the idea here was to create a special PMU for CERN. And because we couldn't use our standard technology that is based on the Rogowski coil. So we had to use low power CT in series to the already existing CTs. So this is what we developed. There is a current CT that measures the current. And then on the secondary of this CT, there is another CT in series that transforms the current waveform into a voltage waveform, to a low power voltage waveform, and then it goes into the PMU. And then, as I said, ELEQ will explain more in depth. So I give the floor to Jérôme for that.
Yeah, Alice, thank you very much for the introduction. As Alice explained, I will also do a short introduction on ELEQ, and then I'll deep dive into the technology we developed here. So ELEQ is founded in 1946. We have 220 employees divided over 2 factories in Steenwijk and Kerpen. And if we can get to see them, Alice, if you click once more. Yes, thank you. And yeah, generally we focus on developing, designing, producing applications to protect, measure, and connect electrical energy within the grid. And to do this, we focus on 4 strategic pillars. In the bottom left, connecting electrical energy with our connection boxes, measuring current and voltage, which is quite important for everybody, I think, within this call. Lean productions. We have the healthy ambition to be as good as the car manufacturing industry, but we are far from that. But you need to have some form of ambition. And a strong mechanical knowledge. So we combine really our electrical knowledge with mechanical knowledge. And by focusing on these 4 pillars, we really strive to supply customers the solutions they require today and tomorrow. If we look into our product portfolio, we have 3 major groups. We have our energy management products. We have our low medium voltage transformers for distribution and billable purposes, and connection boxes for safely connecting public domain lighting or other information systems alongside roads or public transportations. And in all of these 3 portfolios, we really strive to develop and improve with small but also radical innovations. If we look into this project, as Alice already explained, there was an initial project question where there was not allowed to be any footprint on the primary site. So how to reuse the existing and infrastructure for this new application. And the initial idea was something like a CT repeater. So we can just copy the signal, but that's quite a challenging business if you have a primary CT, which is a protection CT. To tackle this tricky business, we were talking with Zaphiro on the topic to come to a product definition. And you can see on the right that the ARM27 is usually used in smaller installations. But here we came to the conclusion that we needed a much more accurate product, which was to be added to the existing infrastructure, as you saw in the picture before, that it was to be added in the secondary circuit. But to do that and to keep an accurate signal, we needed to have a very accurate wide range product. So we established a specification on the accuracy between 0.05 amps on the secondary and 35 amps, and a phase angle that is minimal on a wide range. So really product challenges for us, since we have to deal with physics, are the limited space and the extreme wide range of accuracy. And I'll come back on that a bit later. So this is the initial product definition we had after a few meetings. If we look into the traditional setup, as I already explained, we have a primary conductor where there's the primary current flowing, and then we have a current transformer which gives us a secondary signal, usually of 1 or 5 amps. And this is transferred to a protection relay or power quality analyzer. What we really did here is we tried various solutions, split core CTs, 1M233, 5M233, but also the ring core CTs, in trying to achieve the desired wide range application and to make sure that we have the transfer accuracy that we need while minimally impacting the existing burden, because we do not want to draw all the power away from the initial design intent of an initial design, which is the protection relay currently there. So we tried various ratios and designs, and we tested those also with varying results. To go into the design of a CT. A CT design consists out of 3 parts. It's usually the core, the wire, and a size. If you look into the core material, this really determines the intensity of the magnetic field that can be used to transfer the magnetic energy from primary to secondary windings. What you can see in the bottom are multiple curves, which are magnetization curves. And if you look into the 3 basic materials, there's silicon iron, there's nanocrystalline, and there's mu metal. Those are the 3 traditional materials used. There's also ferrite, but I will not deal with that at the moment. The higher the curve is, so the more on the y-axis the product is, the higher the overcurrent that can be handled. So it can handle much more magnetic energy to be transferred towards the secondary winding. The much more to the left on the x-axis gives the more accurate product and the pickup when it will get, or how do you say that, how it will catch a magnetic field, but also react more accurately to changes. So costs are also an important factor, and physical resilience. So in this case, we went for a nanocrystalline core, which is the blue line you can see exactly in the middle, which would give us as much wide range as possible, but also a very accurate pickup. It's a more expensive core, but it's more brittle, so the physical resilience of the core is not that sturdy. But by giving it an external housing, we were able to use that core in a safe way. And because it's also an LPCT, so under -10, we want to have low VAs because we need to tap into the secondary current. So we need also a core that can pick up the signal early. Then the second one is the choice of wire. The choice of wire usually consists is mainly made on required temperature characteristics. So there's a secondary current flowing, and you have short time current tests and thermal overload tests where you do not want the wire to become a heat element. With an LPCT, you can control the secondary current because of the combination of components. So there's a limit in heat generation, and you can also determine the burden in a sense. There's an impact on the positioning of the winding because also partial winding can lead to partial saturation and can also lead to early saturation of the core. So it's not only the winding, the wire size, but also the positioning of the winding on the core. So the optimal way to wind is to evenly distribute on a round core without air gaps. And that gives usually the best and most stable result, independent of the position of the primary winding, because also the position of the primary winding within CT can be influenced if it's not equally distributedly winded. There's also the option to use thicker wire sometimes. This can help increase the level of saturation a little bit, but we find that the impact is minimal. And in this case, we have a very small CT, as you could also see in the pictures. So going for very thick wire was not an option. And going for multiple wires in parallel is sometimes a way to adjust the ratio error. So because of the iron core losses of the CT, there's a natural ratio error compared to a perfect transformer. And by working with parallel winded cables, you have the option to take off one part of, for example, 2 parallel windings, and therefore compensating minimally the error compared to having one winding and taking one off. So core losses leading to a small error will give us a choice here in wire as well. Last part is size of the product. So as you can see in the formula here, the magnetization properties of the core, which I discussed already, together with the area effect of the core, form a significant portion of the voltage the product can produce if magnetized fully, and also the frequency component cannot be underestimated here. So if you have harmonics within the system which form a significant part of the signal, the core can help. The bigger the core, the better it can transfer higher harmonics. So also here we had to figure out a correct way of designing the product and making sure that we can deliver on the frequencies required. And a general rule of thumb is usually the bigger the CT gets, also the bigger the voltages it can supply, which means the higher the burden it can deliver the required current. In this case, as explained, we have the advantage of an LPCT. That means we need to have a voltage output, which can be achieved on a burden we can choose ourselves. And in this case, the total product burden is in the order of magnitude of 10 to the power of -4. So that means we have a very minimal impact and maximum opportunity for the core to supply the required energy, but also minimal impact on the tapped energy on the secondary circuit of the existing infrastructure. So if we look into the product, here you can see the product data that we agreed upon. And below you can see in blue what the norm usually requires for a product of this type. So in this case, I put in the borders of the class 0.5 product, which means you have 0.5% ratio error on the nominal current. In this case, it's a 5 amp to 1 volt CT. So that means on primary 5 amps, you expect less than 0.5% error. But what we agreed with Zaphiro is that we need an extreme wide range product. So that means here we widened the curve from 0.01 times I primary till 5 times I primary. So that means physics-wise, we have to go from 5 milliamps to 25 amps. This is in contrary to the 35 amps we agreed upon earlier, but I'll come back to that in the results. So yeah, if you look into the testing eventually of this product, we designed the product according to -10. And there's a very interesting point and one major difference between the -2 and the -10. And this is the -10 influence of external conductors. And that means in this test, it's specified that you need to have a conductor of the same size on a 90-degree position from the secondary leads with the same amount of rated current. And then the product is allowed to deviate 1/3 of the norm specified ratio error when introducing the external influence. So that means if we have a 5 amp primary and we make a 5 amp external conductor, the influence on the ratio error is allowed to be 1/3 of the 0.5% that is allowed to have at nominal current. So that means there are 0.1666, etc. percentage of ratio it may allow to be deviate. This is extremely important because, as you saw already in the pictures from Isabel, they are positioned in a very crowded compartment with multiple cables and multiple signals. So having this test within the -10 is extremely important to ensure reliability in these types of applications. Then to the actual measured data. So within our organization, we have multiple measurement labs. And what we did is we measured the entire CT on ratio error and on phase angle. And here you can see the ratio error of the RM27 from 5 milliamps to 25 amps primary. As you can see, we are really well within the band and really wide compared to what the norm states that ELEQ should supply. And the interesting part is here that in the beginning, you can see we are a bit more positive. That has to do with the excitation of the magnetization of the core. And at the end, you can see at 5 times primary that the core is already dipping a bit. So that means the core is slowly saturating. And if you go to the ratio error, you can clearly see that the phase angle at 5 amps primary is shooting out of the agreed request. And this is simply due to the core not being big enough. So if we could have gone for a bigger core, we could have gone for a wider range, but then we might have had a little bit more impact on the lower side. And in this case, we agreed with Zaphiro that there's that this works perfectly for the solution they currently need. And in further designs, we'll see if we can widen this curve. But as explained, it's a great challenge to tackle. And it was a great challenge to work with Zaphiro on this topic. We've had quite a few hassles on it, but I think in the end delivered a great result together. Thank you for the attention there. And back to you, Alice.
Thank you. And so this was basically the presentation, and then we would like to end everything with a demo of our dashboard. So to give you an idea of what are the values that CERN can see. Okay, So this is the dashboard that is available at CERN. So as you can see that there is a part on the left that is a general information about the devices installed. So we can check the measurement, the information about every device, every PMU, communication health, synchronization health. And then the real data, they are in the second module. So in the second column that is called power quality monitoring. Just as a general note, you see in gray asset monitoring and outage analysis. So these are two modules that were not part of this project, so that's why you see it in gray. But in case you want more information about those, I'm happy offline to provide more information. But for this demo, we focus on what was available at CERN in the context of this project, so the power quality monitoring. So in here, if we go in the information about the devices, you can see we can select the feeder. So the 400 kilovolt, 66 or 14, in this case, 18, sorry. We can select the substation. And then based on the selection of the substation, we can see the devices installed in each substation. So for example, here we are selecting a substation SE2, and we can see that these are the devices installed in this substation. We can do the same for another substation, for example, when there are less devices installed, for example, SE1. And then we can see the devices. Then there are some technical information about the devices, some general settings, and in here on the right, we can also select the time frame. The standard is the last 24 hours, but we can also customize it, giving a time frame that we want. There are some pre-selected, like last 30 minutes, last 24 hours, up to last 1 year. In this case, for example, we select last 30 days, so we can clearly see the moment of the commissioning. It's loading. And you can see that we started to record data from, now it's coming, also the second one is loading. So from the 22nd of March, we have data available and we're recording all the data. So in case we want to see all the measurement that happens since commissioning, this is the dashboard to use. In case we want more information about the synchronization, we can go back to the dashboard, to the home, and we can check the communication health and also the time synchronization health. This is the communication health. We are checking and everything is fine. And we can also go back in time and see if there were some issues in the past, for example. And we can do the same for the time synchronization. Going back to the home page, we can go to the power quality monitor. So what is really relevant for this project, for example, power quality events. In here, we can see the list of the events. You can see, and for the moment, purely as a reference, this graph that divides the area basically in 3 areas: a no damage region, a no interruption in function region, and a prohibited region. So on the x-axis, you can see the duration of the event and the amplitude of the event in the y-axis. And all the power event can be mapped, but for the moment, this is not, it's just for reference. And here we can see the list of the events. We can go, for example, we can see some statistic of the events, and also we can click on a single event and have more information on that. We're coming there, for example, we select an event and we can go and see in particular this event. We can see what happened in terms of voltage. We can see in all the time frame. We can zoom and go with the pointer and see the magnitude of all of them. And we also have a message that can also be integrated with the SCADA system. But basically, for example, in this case, we say that the event was a voltage dip detected by PMU2 in substation BCC on the channel VB1. with a residual voltage of 9,286 volt, which is the 89% of the nominal voltage for a duration of 20 milliseconds. So we have a complete set of the power quality event, of information of the power quality event. Can do the same for power frequency variation, voltage variation, so on and so forth. So in here, just give you an overview of what happened with the frequency, but it's possible to have all the information on that. And here it can also be done with the selection of the devices, so see device by device what happened. So that is basically it. As I said before, asset monitor and outage is not something we can see today, but I'm happy to give you more information in case you need. Thank you for your attention.
I guess it's back to you.
Yes, I couldn't find the right camera
Buttons.
and the microphone, so yeah, the buttons. Here I am. Okay. Thank you very much for an interesting presentation. You're right on time. So with the three of you, congratulations. We have now some time for the answer some questions from the chat. We look into that. There aren't really many, but they will come. Maybe they will come. I have a question from James Meyer. How can the RF 2.0 project be used for the energy transition challenge in the Netherlands? I asked you all three, but maybe Alice can be answer the best.
Well, in the Netherlands in general, but I think is also applicable to, so as I said, this project helps us to understand power quality events, so we can better manage the energy, let's say, in this particular project. Then what we see, the real applicability of this project is in private grid operators, but as I said, PMU technology can also be used in public utilities. So I can reply to this question talking about PMU technology and our technology at Zaphiro in general, how we can help the transition, we can help integrating renewables into the grid, so in both private grids and also public grids. So we can give information about the status of the grid, and also we can provide reports and trend reports, also periodic reports, but also trend reports that can help asset managers to better plan the grid of the future. So for example, if they need to integrate renewables, then they have the right information to understand what is the transformer loading, line loading, and to plan it accordingly. So of course is in line with the energy transition and the different flows also we will have in the grids. That is, I mean, different for what was happening in the past.
Yeah, and can you say anything about results you have achieved at CERN or with your tech solutions?
Maybe Isabel can go. Isabel and Mario can go more in detail about that. But just as a brief introduction, so you have seen we are ahead of schedule, but still we have started to collect data relatively recently, so it will be after the data collection that we will have more information, of course. But this is one of the reasons why the PMU have been installed quite soon, because we have to use these 36 months also to collect data. And so after this evaluation of this data, we will be able to have some conclusion on that. And I don't know if Isabel and Mario, you want to elaborate more on what I said.
Yeah, sure. So yeah, basically, as we said before, we are ahead of time. So this is in a sort of initial state yet, And we are still commissioning the system, the software that Alicia showed, and starting cross-checking the results and understanding what information it's providing that we didn't have yet. Of course, the goal is to analyze that data that we get from the PMUs, which is more, it provides a lot of granularity and also a lot of detail on both accuracy and granularity and detail on the different specific points of the LHC loop, and also in this experiment in particular in ALICE. And we also aim for using this data that we get from the PMUs to feed the digital twin. At the end of the day, that's also one of the goals of the project, to develop this digital twin of the CERN power system, so that we can model scenarios that maybe are not the nominal ones, and also model potentially some integration of renewables. That I'm also reading some other questions in the chat. And also another objective of what we want to do with this data is to use it for our immunity studies. So to better understand what are our weak points in the electric grid, what needs to be the focus for improving, and at the end of the day, this is energy efficiency. So it's also applicable to future accelerators, to other industries. We can also take the lessons learned from this and apply to other applications of this technology. Also, we have developed some specific features of these technologies because of the project and because of the specific installation at CERN that might be useful for other applications further and later on.
So we have to ask you, say another over another year for another presentation. But then
we'll come back in 1 year to show the results.
Probably, within a year. And also, it's also interesting because for the other work packages, which are also developing interesting work with solid state amplifiers and permanent magnets, that there's also a work package working on energy efficiency solutions for high power computing centers. These are in a very early stage. The reason why we had to advance it is because we could only open the circuits and install the PMUs during the year-end technical stop. That's when the accelerator is not running, it's not working. And so that's why we are in an earlier stage, but the project is very early stage in general.
I'm really interesting, and I'm really impressed by what you've shown in the presentation. That I would like to see it in real time. So now we're looking at the screen, but I think CERN is really interesting to pay a visit for the people. You are welcoming visitors at CERN, or?
If we are welcoming visitors at CERN for visiting the installations, we have had the project, the last project meeting we had like a month ago, and also Zaphiro came for an in-person meeting, and with them we visited the sites and we saw the installations. Unfortunately, I don't think it's open for the public. Mario, correct me if I'm wrong.
Okay. In general, for the installation that, first of all, I introduce myself. I'm Mario. I work with Mario Parodi. I work with Isabel on this project for CERN. I'm the responsible for the electrical project office in the engineering department. So nice to meet you all. CERN will normally is hosting visitors. Yes, absolutely. You are all. I think all of you are welcome to come because there are visits, there are nice exhibitions, and also nice shows that can be attended with scientific or divulgative content. For the electrical installations, yes, we would need to organize ad hoc visits because, as you can imagine, there is some organization to be done from the point of view of safety also and accessibility. Just as a reminder, being accelerating particles means that we cannot access directly the facilities that are the accelerators themselves, the beam lines, neither the experiments when there is beam, because there is a problem of radioactivity simply. So there are moments during the year, and most of them are underground. There are moments during the year where these are stopped and we can access to perform works, but maybe most important for the visitors, normally, but still to be confirmed, in 2027, every 5 years more or less, CERN does a very long shutdown up to 3-4 years of stop to allow major upgrades of the facilities. And we will have a quite long shutdown from mid-2026 to early 2030s, more or less. So it will be quite long. In the second year, we could count on what CERN calls open days, still to be officialized, but it happened all the long shutdowns before. There, it's a big open to the public to come, and there, indeed, there is the possibility to access also the underground infrastructure to really be in touch, physically touch with the beam lines and the most, let's say, important facilities at CERN. This is something that can be, it will be for sure published, and you will be informed, and you can apply and subscribe, and you are more than welcome.
Well, we would enjoy that, and we keep in touch so that we know when it's possible to pay a visit, whatever. Then I go back to the questions. Even kijken, that was it. Can I compare this? A question from Michael Hartlaar. Can I compare the Zaphiro dashboard software with the Power Spectrum 5 from Siemens?
Yeah, I mean, we can for sure go more in details about the differences we have. Just to briefly answer, I mean, our main differentiator is that we provide an integrated solution, so hardware and software. It's based on PMU technology, so this is also the main difference, is the quality of the data and also the capability of reconstructing the waveform, thanks to the fact that we take measurement every 20 milliseconds. And also, as I said, the fact that we provide both hardware and software, even if our software is also open to integrating third-party devices. Then, of course, I mean, we can go more in detail, but I also wanted to take the opportunity to answer to the previous question, like what happens if somehow jumps GPS. So we are resilient to that because we also, our receiver, they support multiple constellations. So not just GPS, but also Galileo, GLONASS, and others. So this, we are resilient to that.
Mm-hmm. And a question about GPS and a question from Eric Busking. What happens if some autocrat jams the GPS?
Yeah, this is what I was saying. We are resilient to that, so we are open. Our receiver, they support multiple constellations, so there is it's fine. Okay.
Then again, James Meyer, how can the RF 2.0 project balance the push for high energy physics and research with the growing society pressure to reduce the carbon footprints and energy intensity?
Well, of course, as we mentioned before, one of the initial goals is to use the lessons learned in the scenarios that we model and all the insight that we get from our energy efficiency and how to improve it to draw guidelines for future accelerators. So I think it's pretty straightforward in that sense. In an initial stage, for example, applying to the FCC, to the Future Circular Collider, and also the integration, because I mean, we're only talking about the Work Package 4, but there's other efforts ongoing inside the RF 2.0 project. And also we would like to be able to benefit from the studies and the modeling that's going to be going on for integrating renewable energies and energy storage in this kind of computing centers and particle accelerators in research facilities in general. So that would be the main thing I would say.
Okay. And I just another question from Job de Man. What does the load profile of the LHC actually look like? Is it a constant load during the test sequence? And another question is, and are there already special measures taken needed to the CERN grid to shield the LHC from PQ effects coming from the supporting systems balance of the plant systems?
Okay, I'm sorry, I will start with the first question. So the LHC load profile, so for the accelerators we have, let's say, general loads, which are the ones that feed the infrastructure. And then we also have pulse loads, the machine loads, that could be the cryogenics, the pulse loads of the magnets, the RF. So of course the load profile is different for ones and the others. So for the pulse loads, of course, there's a lot of harmonics, there's a lot of but there's a lot of electronic-based equipment there. And then as for the constant load during a test sequence, no. So the accelerator complex that I showed before, it has a complex schedule where the particles go from one of the accelerators to the next one in different, let's say, in different runs or in different turns. I don't know how to call it. And so far as it goes farther in the chain, the whole processes of inputting the particles inside the accelerator, accelerating and then colliding and then taking the particles out, is longer every time. So the profile depends on in which point of that process we are in. And then I don't know if you want to go further in detail.
Yeah, we would need probably a bit more of time, but let's say that already during what it is called an experimental cycle, let's say, if you depending on the accelerators, we have really different behaviors. LHC itself, that is the biggest accelerator that we have, is pretty constant. It means that during the hours where it is filled with beam, the load is quite constant. We speak of a duty cycle that is of more or less 8 hours, just to give you an idea. So with hours of experiments, it means the beam is running. There are 4 interaction points where the beam is colliding. And so this is kept quite constant thanks to a RF system, a radio frequency system that is accelerating the particles to cope with the losses that are mainly due to synchronous radiations or radar losses. So it means that we are able to keep quite but the losses are not so big, so they stay quite constant. The load is quite constant. There is a ramp up to get there that indeed starts from a quite low value to up to the nominal values of LHC, that the maximum stage are around 100 megawatt, more or less, and then there is a ramp down. So we have these cycles of many hours, but when there is the top of the cycle, we are at quite constant load. But to inject, as correctly Isabel was saying, to inject in LHC, we have other machines that are have much more burst profile. For example, the super proton synchronous, that is the ring, the accelerator that is just before, that needs to inject the 2 beams on the accelerator of LHC, because we have two beams running one against the other. So clockwise and counterclockwise, you need an accelerator before that is injecting 2 beams in 2 directions. This is a ring shorter, but the pulses are much higher, and I would say the pulses are much shorter. The duty cycle there is more demanding because you speak of a duty cycle of around 7 seconds, with the top of the cycle up to 90 megawatt of active power of demand, and more or less a quite similar value, tens of megawatt ampere reactive of demand for what concerns reactive power. So we have this load, this pulse load. For what concerns the active power, it's a pulse that indeed the grid operator sees as well. So we are demanding to the grid this 90 megawatt each 70 seconds for a few seconds. So there is this quite demanding load. For the reactive power, also to help the grid operator, and this was a chosen done many years ago at the time of the construction, so it's not recent. Indeed, there is a compensation of this burst load with the 3 SVCs that are installed close to the connection point with the RTE, that are able to cope and to smooth almost to zero, I would say, the reactive power demand. In this sense, we are going to help. We are helping already the voltage regulation, so the VQ regulation of the TSO, not providing these inputs, these cycles that would be maybe not disruptive, because we speak of 400 kilovolt network, so it's quite a strong network, but anyway, they would probably require actions from the TSO. From the active power side, instead, these pulses are visible. So just to give a hint on how it could, it works more or less.
Thank you for your information. Yes, we ran out of time. It's now past 1 o'clock. Yeah, we have to run out of time to answer all the questions, but we will collect them and we will send them to you. Maybe you can answer them, and then we will distribute by email to all the attendees of this webinar. Thank you very much, Isabel, Alice, and Jeroen, for your knowledge and for today's webinar. We will present you our appreciation by a digital present, which will be sent to you shortly. Our next webinar will be the 18th of June and the 17th of September. It's not yet clear which topics will be discussed. On behalf of KIVI, I would like to thank everyone for their interest, and we hope to see you again at the future e-lunch webinar or another activity by KIVI. For now, I wish you a pleasant day and request you to close your Teams connection and leave this meeting.
Thank you. Bye.
Thank you very
Bye-bye.
much. Bye.
Bye-bye.
Thank you. Bye-bye. Goedemiddag.
Hey James.
Goedemiddag.
Volgens mij hadden Alice en Isabel niet door dat zij wel moesten blijven.
Ik had al zo'n donkerblauw vermoeden. Ik zie alleen dat nog dat Kees Noort aanwezig is. We gaan nou